Alright, so in this section we're going to talk a little bit more about the chemical elements, their symbols, and some of their major properties. So 118 elements have been identified, and 91 of these occur naturally on the Earth. So there's a 1 or 2 letter shorthand that's used for each element. In this shorthand, the first letter is always capitalized, and the second letter, if there is one, is always lowercase. So when you're writing out the different elements, you have to use this stipulation. So if we look at the periodic table, let's bring it back in here for a second. So if we're looking over here and we see chlorine would be a good example where there are 2 letters that are going to represent that element. The first one is a C, and it's always going to be represented as a capital C, and the L is always going to be a lowercase l, because it would get confusing if you didn't use the lowercase position for the second letter. For example, if we see a compound like scandium, for example, which is big S and little c, if we wrote this as big S and big C, we would get confused because the big S stands for sulfur and the big C stands for carbon. So if we wrote S and C next to each other, both capital letters, I would think that you mean that there's 1 sulfur and 1 carbon atom in that molecule. Instead of saying, oh no, I really meant scandium, which is a big S and a little c. So you have to be very careful when you're writing out your different elements. If it's an element that's represented by 2 different letters, that second letter has to be written in the lowercase form. So you will get marked off if you do not have this correct nomenclature for the different elements, because you won't really be saying which element you actually want to identify. So most of our symbols in the periodic table are based on the elements' commonly used names. So a good example again is carbon is represented with the big C, very easy to remember. Nitrogen, oxygen, fluorine, chlorine, sulfur, phosphorus, all very good and representative. However, there's some that are named based on their Latin names. So Na, for example, stands for sodium. So that one's a harder one to remember. And same with Pb for lead or Hg for mercury. These are all coming from their Latin terminologies. So when the other most common symbols have already been used, they utilize the Latin names to represent these chemicals. So this is just showing that there are different abundance of different elements that are present on the Earth. And there's different concentrations in different organisms, and there's different concentrations of these elements in outer space. So depending on where your location is, you're going to have different concentrations of the different elements. Within the Earth's crust, the most common 2 elements are going to be oxygen and silicon. So you can see oxygen makes up about 46% of all of the atoms that occur within the Earth's crust. Silicon makes up about 28%, and then aluminum, iron, calcium, sodium, magnesium, potassium, titanium, and hydrogen are the next most abundant elements that we can find in the crust of the Earth. Within the human body, oxygen is also the major component. People find that pretty striking, but this is true, and you will find that about 70% of the human body is actually made up of water. So in between our bones and our muscles and all of the different cells that are maintaining our body is this massive amount of water that makes up the inside of the cell. It makes up all of the major waterways in the body, like the bloodstream and the lymphatic system. Things travel around in water. So water's major components are hydrogen and oxygen. Oxygen making up the bulk at 61%, carbon at about 23%, and then hydrogen is the next most abundant at 10% of the body mass. And then these other components are also going to be important in more trace amounts, such as nitrogen, calcium, phosphorus, sulfur, potassium, sodium, and chlorine, among other more limited minerals. So our symbols for the elements can be combined then to form chemical formulas, and we've already been talking about water quite a lot as being made up of 2 atoms of hydrogen and 1 atom of oxygen. So our subscripts are going to show how many atoms of the smallest fundamental units are within each molecule. So if we have a molecule of methane, methane is CH4. That's going to contain one atom of carbon. So if the subscript is not shown, it indicates that it is a 1. And hydrogen, there's 4 of these guys. So there's 1 atom of carbon and 4 atoms of hydrogen. In this compound here of C12H22O11, 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen are going to be present. So the periodic table then is divided into 3 major regions. So we've got 3 major types of elements that we can have. They fall into 3 major classes. The first class are the metals, and they make up most of the elements on the periodic table. So all of these elements over here, you notice hydrogen here is in blue, and we'll talk about that in a minute. But all of our pink elements here are all considered metals. So most of the elements on the periodic table are considered to be metals. There's a few elements here that are localized here in this purple region. These guys are called metalloids. And then you've got these blue region here that are called nonmetals. And hydrogen is shown in blue here, but it's placed over here with the other metals because it's very unique. It's got some properties that make it behave like a metal, but it also has some properties that make it behave like a nonmetal. So depending upon which situation it's in, hydrogen can kind of be a little bit fickle and act like both. It's going to be a special element. And we'll talk about why that is when we start talking more about the atomic structure of hydrogen. But just note that hydrogen is kind of an exception to the rule. It can behave like these other blue elements over here, like a nonmetal. The metalloids kind of have properties that are intermediate between a metal and a nonmetal, so they form very unique different types of compounds. And it actually, even though they only a few of these guys on the Earth, they actually are very, very important components. Do you see anyone in there that you guys have heard about before? Hopefully you guys are picking out that silicon is actually in there. And we said that that makes up a huge major portion of the Earth's crust as well. So it's a very abundant element on the Earth. It also has been critical for our development of computer technology. Our computer chips are largely based on this silicon platform. So you've all heard of Silicon Valley in California. That's because they specialize in making the computer chips that we constantly are using in our computers. So because it has properties that are between the metals and the nonmetals, it actually is a superior substance for developing these very, very small chips that can be utilized to house vast amounts of information that's stored in our computers. So the metalloids, even though there's only a few of them, silicon is one of the most abundant elements on the Earth, and it has very unique properties that make it different from metals, also different from nonmetals that can perform very important functions within our society and technology. So the metals then are our biggest class of elements. 94 of the known elements are metals, and they always are going to be placed on the left side of the periodic table. Typically, they're going to be solids at room temperature. There's only one exception. Mercury is a liquid at room temperature. It's the only metal that is liquid at room temperature. Usually, they are lustrous when they are freshly cut. So if you cut them, they have a nice lustrous surface. However, they will react quickly with oxygen and they'll rust or oxidize. They'll have a chemical reaction that goes on with oxygen. And so they can dull or take on an oxidized appearance fairly quickly. Typically, they are good conductors of heat and electricity, and they're malleable rather than brittle. So if you take copper wire, for example, you can bend that without breaking it. You can also do that with other metals like silver and gold that you can use for making jewelry. They're very malleable and they don't break very easily. The nonmetals, on the other hand, contain 18 of the known elements, and they are at the right side of the periodic table. 11 of these guys are gases, 6 are solids, and 1, bromine, is a liquid. They're typically, in comparison to our metals, they're poor conductors of heat and electricity, and they're typically brittle in their solid state, and they'll break very easily. The metalloids, again, there's only 6 of the known elements that are metalloids, but again, silicon is going to be one of the major compounds in the Earth's crust, and they have properties, again, that are intermediate between the metals and the non-metals. They're going to occur in that zigzag band between the metals on the left and the non-metals on the right side of the periodic table. So again, if we go back and just take a look at our periodic table, again, these pink elements are going to all be the metals. The metalloids shown here in purple, and the non-metals shown in blue in this region. So we'll just say a few things about mercury and about mercury poisoning. So remember, the symbol for mercury is Hg. Mercury, again, is the only metallic element that's a liquid at room temperature. And so it has many uses in which it's not toxic. So the laxative calomel is Hg2Cl2. So there's 2 atoms of mercury combined with 2 atoms of chlorine. And when it's in this form, it actually is not dangerous. And then we also use it in dental amalgams when we do fillings in the teeth. There's been some indication in the literature that should suggest that maybe mercury fillings aren't the best for us, but they've been unable to show that any of the mercury is leached out of the amalgam to cause any health effects. So mercury does have uses within our population where it doesn't have toxicity. However, mercury can be very dangerous, and exposure to things like mercury vapor can cause very adverse health effects. So the toxicity of the mercury is really related to its solubility within the body. The mercury vapor can accumulate in the lungs, and it slowly becomes soluble over time. And it's this solubility within the body that can cause the problems, because soluble mercury can enter into the bloodstream and it can interfere with various biological processes, especially within the brain. So an example of this was in the hat industry, and mercury was used then in the process of curing felt that was in some hats. And so the hatters that would actually be building these hats and making these hats, they would be exposed to some of these toxic fumes or vapors of the mercury during this curing process. And when they became soluble in the body, they would actually go into the brain, and they would actually cause neurological damage. And so this could include confused speech or distorted vision, for example. And so this got the terminology or name as Mad Hatter's disease. So people would often say, oh, you're mad as a hatter. Because they would end up kind of going crazy at the end of their careers due to this mercury exposure. So now we want to just end this section by showing you an example of a chemical reaction or a chemical change. So this is where the chemical, in this case the nickel, is going to be physically altered into a different form. So nickel is a hard, shiny metal. So you can see it down here in this diagram here. So hydrogen chloride is a colorless gas that can be dissolved into the water to form hydrochloric acid. And so you see this hydrochloric acid solution over in this container here. So if you add hydrochloric acid to the nickel, there's a chemical reaction that will occur that will cause the nickel to form a new compound with the hydrochloric acid. So we can see evidence of this because the solution actually turns green, and we actually can have gas bubble out of this reaction mixture. So in this case, the chemical reaction takes place, and you can see that there's an indication that the reaction is taking place. The hydrochloric acid was a clear solution to start with. As this reaction proceeds, you can see that there's a color change. So that's our first indicator. You can also see that there's these little bubbles that form too, suggesting that a gas is escaping as this reaction takes place. So you've got change in color, dissolving of the nickel. If we wait over time, we'll see that our solid nickel will slowly dissolve into the solution, and you have the appearance of the bubbles. So these 3 things that we can visualize indicate that a chemical change is going on here, not just a physical change. So anytime there's a chemical change going on, we can write it as a chemical reaction. So there's something going on that is changing within the reaction. In this case, we've got the nickel and the hydrochloric acid. They're going to be our reactants on the left side of the equation. When we mix these two together, they're going to form new things. In this case, they're forming the nickel 2 chloride. So this is a new compound, a mixture of the things that were in this side. And then we're going to also have hydrogen gas that's coming off. And these are the bubbles that are being formed. The nickel chloride is the green compound that we are visualizing that's formed that color change. So in this case, our elemental nickel, that's the solid that we had, and the hydrochloric acid, the clear solution that we showed in the last diagram, is going to change to the green colored product, nickel chloride, and the evolution of the gas bubbles, hydrogen gas coming off. So we'll learn how to actually build our molecules so that they have the correct formulas in here. But you can see that we can represent them by words, so by their names, or we can draw them in their elemental form as these forms of compounds or the actual elements. And we will stop here for this section.